Uh, Good afternoon, everybody. Uh, Welcome to the Lehigh University Energy Systems Engineering seminar series. This is the second of 8 seminars that we'll have this semester. And so I'm very pleased to welcome Frank Felder. He will be talking about resource adequacy modeling and policy, data centers, and electricity load growth. It's a very it's a very topical study, especially since we have so many activities and large loads. This has a big impact on resource adequacy and so on. So to present this is Frank Felder. He's a principal and independent electricity consultant and a senior fellow at the Oxford Institute for Energy Studies and a visiting researcher at CAPSARC, an international energy think tank. Formerly, he was a director of the Rutgers Energy Institute, research professor and Center for Energy, Economic, and Environmental Policy at the Blaustein School of Planning and Public Policy at Rutgers. He actually teaches and researches electricity markets and the reliability and resilience of power systems. Frank holds a doctorate in technology management and policy from MIT. So Frank takes the stage, I just want to go over some housekeeping items. This lecture will be for about 1.5 hours, nominally split 1 hour for presentation and 30 minutes for Q&A. And when the Q&A session, I'll give first dibs to students. Students will be requested to ask questions, and then I'll have the general audience participate. So with all that, thank you again for attending the second seminar. Frank, the floor is yours.
Great. Well, thank you, Rudy. Thank you, Susan, and the Lehigh University and the Master's Program on Energy Systems Engineering. It's good to be back. As we were getting set up, Rudy and I were talking about what has changed in a year. So I gave a similar, well, I wouldn't say similar presentation. At first blush, it would be similar. It was on resource adequacy and modeling and policy. About a year ago, at least in the US, so I'm not speaking globally, the question was resource adequacy, but the question really was how to integrate wind and solar and energy storage into these models, into the grid, and to meet this portion of reliability requirements. Now the world has changed, and we'll talk a lot about that. Partly change in federal administration and priorities with respect to clean energy and climate emission reductions. But the other piece has been, literally in the last year, a rapid increase of these large loads. And although they're not exclusive data centers or AI facilities, for the most part, they are. So the term data center and large load aren't synonymous, but for a first order, they are. So anyway, I'm going to first talk about what's going on in our region of the country, PJM, the kind of mid-Atlantic power system and market, and some activities I've been involved in. Those are just my own views, not on behalf of clients. I do work for the Pennsylvania Office of Consumer Advocates on this topic, among others. But I'll keep it to my views and not anyone else's. And then secondly, I'll delve deeper into the modeling and the connection between it and policy. What I like about this topic, besides just the importance, having a reliable power grid is just a prerequisite for a modern economy. But just the interplay between the technical details, and there I mean both the engineering and the economics, as reflected in conceptual frameworks. How do you calculate what is resource adequacy? How do you calculate it? What do the models include? What don't they include? How good are the models? Kind of the details that are very important for the modeling. But that connection between those modeling outcomes and how they inform or don't inform policy, and to what extent they should be informed policy. So we'll get into all that, but I think it's a great example, not the only example, of connecting technical issues and considerations and thinking with broader policy and how those things fit and don't fit together. Okay, so with that, reliability has been in the news over the last couple of years, particularly resource adequacy. So in short, resource adequacy is the probability that the power system has enough supply to meet demand. Now, for electricity, you're worried about that for a variety of reasons, but one is the power system has to match supply and demand almost instantaneously. Any slight deviation, a more than slight deviation between supply and demand uh, results in changing frequency. And typically the problem is you're worried about more demand than supply, because when the reverse happens, you have more supply than demand, you can always reduce your generation by opening a breaker, so to speak, and bringing those two back into equilibrium. But it's the reverse problem up until now that has been the focus, having more demand than supply and to avoid cascading outages. So where frequency of the system drops, that triggers generations to trip units to trip offline because their control signal, they're synchronized to the grid based on the frequency. And you get these cascading outages, and the concern is large scale blackouts. So resource adequacy is an important piece of reliability. We'll get to that in some more details. And in the current context, today in the US and elsewhere in the world, and in particular in kind of our region, so the PJM, kind of the mid-Atlantic and mid part of the Midwest power system and its neighboring systems, such as the Mid-Continent ISO Independent System Operator, are basically short supply for a variety of reasons. And we'll go through those. And those have all captured the headlines. Some of it has to do with retirement of aging generation units, that were built 60, 80 years ago, and just aren't economical to continue to refurbish and maintain online. Some of it has to do with installing renewables, intermittent renewables, variable renewables, solar and wind. Some of it has to do with the time it takes to interconnect a generation unit to the grid. And in the last year, much of it has been just the increasing demand and requests for large loads, these data centers or AI facilities, to interconnect to the grid. And you'll see some examples of the data coming up in terms of these forecasts, how there's been literally a step change in the last 12 months in terms of these demand forecasts. Here's another set of headlines. Maybe a couple months ago, the U.S. Department of Energy released, it's been criticized, but like most reports, but maybe this more than others, in terms of the impact, the resource adequacy concerns, at least that the Department of Energy has, given the things I just outlined. And you'll see when we talk about PJM, which you'll see a map in a moment, but basically 14 states, Mid-Atlantic, Midwest, that region of the power system, which is also one of the world's largest wholesale electricity markets, has had a huge increase in requests on the order of 32 gigawatts, 32,000 megawatts of requests demand forecast in the next 5 years. So it's just a huge increase in demand. So you bring together a tight power system and large increase in demand. Any capital intensive industry, natural gas, power, football stadiums, anything, infrastructure, highways, you start quickly overwhelming the system. The problem with electricity is, as I mentioned, if there's too much demand for supply, not only are some customers not served, the excess demand, but if that problem is not managed correctly, both in operations and in planning, it can lead to preferably rotating blackouts, controlled disconnection of load, or even worse, these cascading outages that risk bringing down large parts of the system. So it's a timely and very important problem. Here's just one more set of in the news. And underneath of this, in part, is rethinking these resource adequacy models. and to what extent they should be informing policymakers, and then what to do about what are the responses to impending or predicted or forecasted power shortages. Okay, so here's just an example of forecast. If you look from 2014 to pretty much 2024, you see flat, basically flat across the whole entire sector, residential, commercial, data center, and industrial. You know, data centers have been a part, and I've had doctoral students in, you know, 10 years ago were doing studies, you know, and the motivation, part of the motivation was the increase in data center load, going from, you know, 0% to becoming 5%, you know, over a 20-year period. So where it's, you know, it's worthy of its own kind of subsector or its own designation within the load forecast. But the real break in terms of this, so it's been a slowly growing portion of electricity. Data centers obviously are heavily electricity. They're just basically rows and rows and rows of computer chips, you know, just banks and banks of computer processing, and they depend on electricity. Then you add in the cooling because they generate huge amounts of heat. So just think about putting your hand, being careful underneath your laptop or near your laptop. You feel the heat, particularly when you're processing a lot. But then you have banks of this in a confined area. You need to cool it. That depends on electricity, and so forth. So in the last year, you start seeing this large increase. Now, in the electric power system, it's slow moving. It's like a battleship or aircraft carrier. It's hard to switch directions quickly. So going from a 0 or near 0% load growth to 2 or 3% over 5 years, just by compounding, if that load forecast continues, that increase in load growth, then you can have in 5 years these dramatic needs, assuming the forecasts are correct or reasonably correct, in expansion, so of generation, transmission, and distribution. Um, so it really presents a challenge to the system. Um, and if you think about it, the power system and infrastructure is pretty much a global supply chain, transformers, wires, conductors, workforce training, technical competence, and all the associated supporting equipment and gear. And other parts of the world are emerging economies are rapidly increasing their uh, power system build out. Other parts of it, like in Europe, are transitioning more towards zero emissions. So worldwide, there's a large demand on the equipment and expertise and trained labor force for this. And then you add in, you know, the build out in the U.S., which is, you know, about a quarter of the world's economy. So it's substantial. This graph overdoes it. This is for data center forecast, and you see this just this break, this knee in forecast. Now, what this graph should include, but it doesn't, but it's hard to, is some type of error bars, right? So, you know, kind of if you were to draw a normal error bar or just around this one, you know, some type of error bar. The US and other parts of the world have had large annual forecasts of electricity demand. So an emerging economy would grow at 6% electricity and maybe 10% GDP, 8% GDP, something like that. The US did that in the 50s and 60s. Um, but then the US did that, and in the 70s, late 70s, early, well, 70s and early 80s, we had an economic recession for a variety of reasons, and those large increase in forecasts and the perspective, the anticipated build out of the system were not needed. And that created a surplus of generation transmission and distribution assets because they were built, you know, today, assuming a 5% forecast or greater, to be ready 5 years from now. 5 years from now, the load doesn't materialize or completely materialize. You have what in the industry is called stranded investment. So these estimates of increases in gigawatts, so just capacity, vary depending on the studies for the next 5 years or so, but US wide, 30 to 90 gigawatts. Now, some of this is speculative. If you're a data center developer, You may develop multiple data centers at different locations within the same power system, PJM in our case, but even across power systems, PJM in the mid-continent, ISO system, and or within the same state. Not all your development projects are going to come to fruition. You may not get the zoning treatment that you need. Tax policy may change. Um, the option on the land you had expired before you could exercise it, or just business planning changes. So it's not surprising that developers of data centers may be, developing multiple sites with the anticipation that only a few or some percentage of those sites are actually developed. That's the same with generation. A generation developer may be developing a solar farm or wind farm or gas turbine in multiple locations, and then only expect to have, some percent of those developments actually get developed on time. Some may be developed but get delayed. Some may not be developed at all. So some of it is speculative, some of it's redundant, and some of the capacity is not true demand in the sense that data centers tend to ramp up to their nameplate capacity over time. They may not operate at fully at 100% for a variety of reasons and so forth. So trying to get all these forecasts and sort through and distill kind of what's realistic in the near term and forward is a challenge. And so this issue of load forecasting, which is a key input to a resource adequacy model that we'll get to, um, is just really tricky. So a year ago, I think people were doing studies a year ago or 2 years ago were putting in relatively flat forecasts and not really considering, because history, recent history at least, didn't support a large increase in forecasts like we're currently seeing. So there, the model could be a really good model, but if its input assumption, a key input assumption, load forecast growth is off, um, then obviously the rest of the modeling results are off. Okay, so reliability is in the news for a variety of reasons. I mentioned AI growth centers, variable wind and solar, planned retirements, interconnection queues of generation units. Another big issue I haven't mentioned is just building out the transmission system. So over the last 100 years in the US, the grid has emerged organically, and it's slowly been more and more interconnected, blocks of a city to cities, to states, to regions, right? So that interconnection, as we make the transmission of electricity more and more cost effective, you can transmit it 500, 1,000 miles cost effectively, then building out the transmission system to achieve economies about load diversity, to balance intermittent resources across larger regions, to support reliability, to increase inertia, and so forth, is a big piece as well. And of course, in the last 5 years or so, there's been, and even more recently, a lot of concerns about blackouts, resource adequacy. The big one was in Texas or ERCOT 3 or 4 years ago, and where demand just outstrips supply. Okay, so I want to spend a little time just on the ground because I think it'll motivate and it'll raise a lot of issues that are just relevant. And then to the extent in the last 30 minutes of the presentation mode, I'll delve in more into resource adequacy policy and modeling. And then I'll leave it the last 30 minutes for Q&A and discussion. So there's a lot on this slide. Part of it is just a map of PJM. So PJM is 14 states or so in the District of Columbia, 20 or so, 25 utilities across its footprint. It spans at least 2 time zones. It's about, you can see some of the data here, but it's roughly 200 gigawatts. The forecasts are, depending on which forecast, for an additional 32 gigawatts or something like that, 30 or so, 30 plus gigawatts in the next 5 years. The load growth had been traditionally flat or 0.5% a year. Now the most recent numbers are, three to four, or high 3% per year. So just think of the compounding even over 5 years, if that sustains itself. Of course, there's load growth in terms of megawatt hours or gigawatt hours, and also in terms of gigawatts. And those have different implications in terms of the build out of generation, transmission, and distribution. Um, so what are the issues? So PJM a week or so ago, and again, I'm going to try to be as neutral as I can, um, looked and said, there's all these requests to the local electric distribution company. Typically, these large loads are connected on the distribution system, but some could be connected on the lower voltage transmission system. Requests, these EDCs, the electric distribution companies, are getting all these requests to interconnect load. And these EDCs then take these requests and then they submit those requests to PJM so PJM can develop a load forecast over the next 5 years. That load forecast sets in part the amount of generation that PJM needs, including an additional capacity margin, additional inventory of generation to meet peak load. So PJM, like many systems in the world, goes through a process of figuring out what peak load will be 3, 5, 10 years out. And then from that, that's an input to determine how much additional generation above peak load needs to be built to account for the random outages of generation units, right? So that's the reserve margin or capacity margin, typically around 15%, something like that. It varies by system and a variety of issues. So PJM puts these numbers into its resource adequacy. Now, PJM has one other wrinkle that other parts of the US, although some do, and certainly other parts of the world don't do. It's an electricity market, a wholesale market, and it has a capacity product, basically a requirement that load serving entities, the final entity that buys power to serve end use customers, commercial, industrial, residential, buy enough generation plus extra capacity, their share of the capacity margin, to meet demand, to meet the region's resource adequacy requirement of not having to disconnect firm load more than one time in 10 years on a planning basis. And so with that, you now input a dramatically higher load forecast that pushes up the amount of generation that needs to be built, plus the reserve margin, which is a percentage of that. So you have a compounding effect. And as this works through how PJM's capacity market works, not surprisingly, you increase demand dramatically. And if supply is short or in equilibrium before you increase the demand, prices spike. And in a market, assuming no market power, which is a big assumption, during scarcity, economists want prices to go high to signal both the supply and the demand, both supply and demand, to build more capacity. So the PJM capacity market prices have gone up dramatically as a result of these forecasts that may or may not be solid for some good reasons and some less so good reasons, right? Because of speculation or duplication or just exuberance, right? Maybe people are over forecasting the potential for AI. So this raises very serious concerns. So one is electricity is not your standard good. It's what economists would call merit good. It's almost a necessity. A lot of times you'll hear, particularly in modern economies, policymakers talk about electricity being a necessity, almost a right, like healthcare and housing. And understandably so. In a modern economy, it can be deadly not to have access to electricity, as we in US unfortunately demonstrated several years back in Texas and elsewhere. So the public policy process, this isn't just, the price of avocados go through the roof and people buy less guacamole at their local restaurant or supermarket. This is a necessity or viewed as a necessity of life. So it has large public policy implications. It affects everyone in, where prices are going up, and residents tend to vote in a democracy or a republic. And so it has just a direct political implications. And there are numerous examples in history, I won't go into them, in the US where governors, weren't governors anymore because of high electricity. And you add on to that the potential of blackouts or rotating power outages, which in the press are blackouts. um, that's a double whammy. Why are we paying higher prices and not have electricity? That's a very hard question for a politician holding office to answer. And it's a very easy question to answer if you're an opponent. So it takes on, and rightly so, I'm not trying to be dramatic, political overtones. We need a reliable and affordable power system. Why can't we do that? That's a legitimate political question. And because the power system in the US and in some places as elsewhere as well crosses multiple jurisdictions, local, state, and federal boundaries. So PJM is regulated by the federal government, the Federal Energy Regulatory Commission. It creates this additional wrinkle. There's not one single jurisdiction that has a problem, that can solve the problem. A municipality cites data centers. It says, yes, you can cite your data center here based on our zoning laws and our master plan for development. It's the states who regulate resource adequacy and require utilities to provide affordable, the word's different by statute, but basically affordable and reliable power. And in many states, states require utilities to serve all customers who show up. So the state just can't decide. If someone knocks on my door and says, Frank, we want you to do this consulting project, I can say, typically I don't say no, but I can say, no, I'm going on vacation. For the electric distribution company in many states, they're required to connect that customer, and based on in a prudent and good way, sound engineering way. So the electric utilities just can't turn away load, even if they wanted to. And there's also a lot of consideration for the economic development impact of these data centers, the construction jobs while they're being built, the jobs during their operations, which are smaller but still important, the property tax implications. If you take, so many acres and chock it full of computers, the property value goes up on that square acre on that piece of land, and so that's very enticing to municipalities to tax. Um, uh, for the tax base, and therefore is important. So you're in effect trading off these very important considerations of economic development. You can think of data centers in a way, and these AI, as a remanufacturing. Since the late 60s, almost many politicians, if not most, advocated for bringing back the industrial base, the manufacturing base to the US. You hear that now. You certainly hear it in states like Ohio and Pennsylvania that had large manufacturing bases that in the 70s were dramatically reduced due to some of the reasons I talked about, alluded to. And so you have this prospective economic boom, but with implications for the reliability and cost of the electric power system. And then there's some other implications elsewhere, other environmental issues, water, noise, traffic patterns, kind of the whole slate of issues that come with economic development, and the pros and cons and the different views about that. So what is PJM to do? So PJM a couple of weeks ago released a proposal to say, why don't we consider to all of its stakeholders, right? To all of its members, which are generators, transmission owners, distribution companies, independent power producers, traders, sometimes state officials, et cetera, environmental groups, whoever wants to join the PJM stakeholder process. PJM offered a proposal that, at a very, very high level, and probably overly simplified, in part said, maybe we should allow large loads, data centers, to interconnect and not require them to buy this capacity product. So that would save them some money. But if there's more demand than supply, they would be the first to be disconnected. Okay. So roughly speaking, using my words, not PJM, it's kind of a non-firm service, an intermittent service. So, we've experienced this in other parts of our lives, right? You go to Disney World, some people have high priorities on the line, some people have to wait at the back, but they paid a different price for the ticket. Or other arrangements on the gas side where load can be interruptible. They buy non-firm gas. They didn't pay the full freight of firm transportation cost of capacity, pipeline capacity, and their probability of being interrupted increases, but they also paid less. So it's a lower quality service. So there's been some reaction to that by a variety of stakeholders. I won't characterize that, but the issue is, should there be this non-firm product? What are the implications for reliabilities? Will data centers be willing to buy this not, quote, non-firm, it's called non-capacity backed load, non-capacity backed service? Will they be interested if you're spending $1 billion or $500 million on a data center? Maybe you do have some flexibility. Maybe you can bring your own generation at backup supplies. Maybe your sister data center can carry some of the load if you need to ramp down. But to what extent? On the other hand, you like a firm and, of course, low cost source of power because you don't want to have to adjust your operations, due to changing power system condition, particularly when the grid is facing shortages. So this issue is front and center about the trade-offs at the policy level between economic development, reliability, and cost, who gets priority of service when there's shortages. Do residentials get first? Obviously, people agree that critical facilities, hospitals, emergency facilities, those type get priority. But do we shut down data centers or factories before residential or vice versa? Or what's the priority? Who should pay? Is it fair, kind of in human sense, for residentials to pay higher electricity prices because someone bought a large or connected a large data center to the system? So those are a variety of issues. And another one, how should electricity markets be designed, or how should their designs change to accommodate these changes in load? So let me stop there, and that's the real big picture. But that big picture then filters down into the modeling considerations, the more of the technical, both engineering and economic considerations and resource adequacy models. So let me stop there and see if there's any burning question. We're good. Definitely have plenty of time at the end for questions and discussions, but if there's any burning question that is preventing someone from getting on board where I'm going next, now
We
would
have
be
a question in the chat box, Frank. Let's see. Frank Richard. Uh, how can regulators and PJM allow sale of existing output like Susquehanna and the nuclear, a hydro plant in Pennsylvania, to power these data centers instead of all the other loads they normally supply?
I won't specifically answer that question. It does raise a topic that I alluded to but didn't fully develop, which is, and it goes under the heading of BYOG, bring your own generation. So one of the approaches, and PJM recognizes this, but other stakeholders as well, should we allow these large loads, these data centers, to bring their own generation and give them priority to interconnect? In other words, if I'm developing a data center and I just want to connect to the grid, and Rudy's developing one, but at the same time, he either has a contract with a large nuclear power plant or plans to build his own generation nearby, and we can talk about what nearby means or should mean. Does he get priority? Should he be interconnected before me? Should he be able to avoid not this non-capacity option being imposed upon him as a last resort? So this notion of bring your own generation, and since these data centers are large, 500,000 megawatts, and since many of the owners, although they may be shifting, want to have strong greenhouse gas commitments um, to reduce them. They want to be able to interconnect either with nuclear or co-locate is another term, their data center with nuclear or solar and batteries or a combination or maybe clean type of combustion turbines or diesel, engines. So that whole issue of should priority be given to data centers or large load that are also developing or have developed or have under contract their own generation. And then that gets into the issue of, why do we have a grid? Should we have, which I started out talking about the benefits of a grid. We have grids over large regions for a variety of reasons. They improve reliability, they reduce cost, they allow for the integration of renewables, variable renewables. Should these data centers just set up their own industrial park isolated from the grid or only connect to the grid under certain conditions? Is that more cost effective? Is that good public policy? What does that do to the rest of the grid and so forth? So I won't answer that question, but I do want to emphasize it's a very good question. And some of the stuff we'll get to develops some of the tools or parts of the tools that could help address that question.
This is a related question that very strikes the very heart of the debate that's going on. Do data centers have lower electric rates from residents?
You would have to look at jurisdiction by jurisdiction. Typically, so you'd have to look at their transmission, distribution, and generation. So it depends in part if they're in a market. If they're in a market, they're buying power from the same wholesale market. Now that may vary by time and location. So, that's set by the wholesale market. So Frank Felder, if I was located right by the data center in PJM, and bought power the same time that the data center was at the wholesale level, I'd be paying the same price. But the T&D cost could be different. If you're in a non-market, it depends whether or not how the utility sets up its industrial rates. Typically, large industrial rates and fully vertically integrated utilities are less than residential, although some jurisdictions do have what maybe a pejorative term, cross-subsidization. Industrial customers take voltage at a higher level than residential, so they need fewer transformers. That saves on a cost. The substation cost, or you don't need additional sub transformers and substations to lower the voltage down to a household level of 120 volts or 240 volts. So that saves on it. You don't have all the residential wires that you need for residential, a neighborhood with many houses. You just have lots of wires, whereas if a data center is near a substation, there's just one wire. You don't have the same, may not have the same distance in wire. It's at a higher voltages, there are less losses, and so forth. So if I were to guess, I would think yes, that these large industrial customers. Now, that being said, many states are developing tariffs where they define or proposing to have a data center class, a large load class, to recognize that there's some very specific, unique costs to these large data centers. Maybe they want to be connected to two substations for reliability. Maybe they have very specific costs that do not benefit the rest of the system, and therefore should be allocated to that data center and not all the other transmission and distribution customers. So that's an active area of how to design tariffs that both reflect the costs of serving these data centers or large loads, and at the same time protect other ratepayers from stranded investments. So that's an incredibly important topic. Why don't I move on? Those are two great
Yes,
issues.
please move on, Frank.
But we'll come back. I'm sure we'll come back to them as we go. For this group, I'll just briefly remind you what capacity is, capacity factors. What are the actual capacity factors of these data center? It depends in part on their model, their business model, what type of data they're processing. Is it AI? Is it business processing or whatever? But typically, you think of these data centers as high capacity, 500 megawatts. Certainly, what was 5 years ago or 3 years ago, a 100 megawatt data center is small in today's world and what's being developed. So 1,000 megawatts is typical. You hear plans for 2,000 megawatt data centers or data center, uh, I guess, industrial parks. Um, and typically, you think of them as high capacity factors. They're going to be running a large percentage of the time. So now people have different views on that and what that actual capacity factor is and what percent of its summer capacity versus its nameplate versus so forth. But typically, as a first order approximation, they're large and they're baseload type loads. New York has a lot of requirements. As I mentioned, resource adequacy is really a state level, but it's implemented in the US by utilities and including the various markets, like the market we're in, PJM, the wholesale market. But roughly speaking, and again, it varies, is this one time in 10 years. So there must be sufficient supply to meet demand so that you don't have to disconnect firm load uh, more than one time on a planning horizon, one time in 10 years. There's different interpretations of that standard, different ways to interpret that standard. But for our purposes, think of it as an inventory requirement. There's some inventory requirement that when someone wants electricity, there's a small amount of time that they're not going to be served at the bulk power system level. This doesn't include distribution. And depending on the region and how they model transmission, it may or may not adequately include transmission limits. Okay. So that inventory policy is then operationalized in a resource adequacy model. So reliability in the US has kind of two major legs. One is resource adequacy. And if you look at the standard textbook by Billington and Allen, they'll divide resource adequacy into generation adequacy, level 2 generation and transmission, and then all three. The problem is these are computationally intensive, even with advances in computer systems. So historically, utilities tend to do this, or maybe these two together, maybe at the interchange level. Security or also operational reliability is the ability of the system to withstand a sudden failure of generation or transmission. Now, a year or so ago in Virginia, there was a fault, a frequency or voltage fault on the power system. And data centers are very sensitive. They really want a high quality power because they're, processing tens of thousands of computer chips. So their specifications of the power quality they want are very tight compared to my home and my alarm clock or my TV. And so the data centers saw a fault or a spike in voltage or frequency. They disconnected, and multiple data centers independently being operated saw the same power fluctuation or power quality fluctuation and disconnected. And so you had several thousand megawatts of load being disconnected in a very short order of time. Now, these data centers just don't disconnect and go black. They have backup power supplies, typically diesel generators, but not necessarily, not always. And they come online and they're designed to come online within 10 or 30 seconds. And then there's short-term storage to bridge that 10 seconds or 30 seconds. But this is a big deal for the power system because if you're a PJM operator or a power system operator, all of a sudden you see 2,000 megawatts of load disappear from the system, right? And that can cause fluctuations and power distortions, just like if you swerve a car, right, on snow or ice, you start getting, you could swerve out of control. And so these data centers bring to bear a type of failure that I wouldn't say no one thought about, but was much less important, which is the disconnection of large loads and its impact on operational reliability or security. Whereas before, for all practical purposes, we were worried about it from the generation or the transmission side. But for today, the rest of today, I'm just going to focus on resource adequacy. So what the power systems have done historically, or the planners, is they say, okay, we think our peak load in 5 years will be 10,000 megawatts. We need to have a cushion because of random outages of generation just due to random failures for whatever reason. Maybe we need a 15% cushion. And so we define either a capacity margin or a reserve margin. It's the same underlying um, excess or inventory, spare, so to speak, except the denominator is different. But it's still capturing, the numbers are different, but it's capturing how much additional generation should we have above peak load, either normalized to generation capacity or to peak load, in order to meet this, this industry widespread requirement of one time in 10 years. Now, there's a whole set of recent discussions in the last several years, and it's active, very active here and in Europe, about should this one time in 10 years or one day in 10 years be the right requirement? Should it change? Should it be based on unserved energy? Should it be adjusted for risk? I'll leave all that to the side for now, but let's assume we have some type of resource adequacy criterion. We need to operationalize that into a capacity margin or a reserve margin. So the way people do that is you define what you mean by resource adequacy. You have some type of metric, this one time in 10 years. You develop a model. A major input is load forecast, but also the forced outage rates of generation units, the expansion plan of generation units, which ones will be built and retired over the planning horizon. How much can you rely upon from your neighboring power pools or markets or utilities? How reliable are those transmission ties? You put all this stuff in a Monte Carlo model, you run these random experiments, and you calculate whether or not you have enough generation plus capacity margin to meet your resource adequacy requirement. Okay, so that's the fundamental kind of calculation. It's an inventory problem, right? Same inventory problem if you're for shoes or for pencils for your office supply room, right? Same idea. This provides a little bit more detail. I won't belabor it. This is a standard model that's been used. It's a GE product, been available since the 1980s, I believe. But there are others. There are open source models. That's great about now. There's a lot of open source models, resource adequacy models that people use. And it just summarizes basically the input: supply, demand, transmission to the extent that's being considered. And then you calculate, do I have enough? And if not, how much more generation needs to be built? So notice the focus is on the generation side. I mentioned very little about demand response. I'm sure we'll get to that in the Q&A, and I alluded to it with the data center flexibility. You can think of that as demand response. So what role should it be? What should be the incentives? How much should you expect a data center to provide in demand response? Those are some of the questions. I'll skip this. I think the PowerPoint will be available to everyone. It just gives more details on models if you're interested in different models and different criteria and what different regions of the US do. Just emphasize that there's uniformity at a high level, but the actual implementation of the models, the criteria, the data sets, the data cleaning, and many other factors that go into these models may not be consistent or may be done differently within the US and internationally. I think I've described kind of the basic Monte Carlo approach. So I'll move on to put into these models, and the output is a probability distribution of generation. You have some load distribution you get from econometric studies or whatever, and then you look for where you have more load, more demand than supply. Okay, and that's a problem, and how frequently this occurs. So that's the loss of load probability, loss of load expectation. So I don't want to say loose with these terms, but just this generic concept of how frequent or what's the probability you have more supply, more demand than supply. Does that satisfy the criteria or not? And if not, what do you do? Okay, so that's the problem PJM is facing. The other wrinkle, which last year I spent a lot of time talking about, I'll spend less time this year, is how do you treat wind and solar? All right. So up until the large introduction of wind and solar, implicit assumption, and this came back to bite planners, I would argue, but put that issue aside, was that the thermal unit or a nuclear units, thermal, were you could turn them on, at least for planning for resource adequacy. So the assumption was there was enough coal by the coal plant that if you needed the unit, you would just turn it on, and then the question is whether or not it would start. But you could turn on the unit whenever you needed to meet reliability, right? Well, with wind and solar, that's not the case, although there are technologies and cost considerations where it could be the case, at least in part. So what happens when the sun goes down? Well, obviously the value of a solar panel, just a solar panel by itself, after sunset in terms of a resource adequacy value, how much capacity does it supply, is zero, right? Now, if you pair a solar panel with a battery, then maybe at 7 p.m., after sunset on a winter night, or 8 p.m. or 9 p.m. on a summer's eve, it has some value because it's charged up the battery. But now these models become more complicated because what has happened in prior hours matters. How sunny it was, how much wind there was, what was the charge state of batteries, how many batteries are there, or other storage devices. When is sunset occurring? What about cloud cover? What about variations in wind? So the fact that what has happened over the course of a day affects what has happened in prior hours, affects the resource adequacy calculation in our now. How much weather variability do you account for? Do you account for expected or many argue changes in climate, which would then affect the weather distribution so that 10 years or 20 years from now could look different from 5 years ago or today? So this adds a lot of more computational because you now have to do these Monte Carlo analyses chronological. You start day one, hour one, and run every hour. In effect, you're doing a miniature dispatch because you have to dispatch the system to figure out how the state of charge of batteries, to then figure out how much the batteries are charged and therefore available when the solar goes out. So this is a very challenging problem, and it falls under the term of ELCC, which is the effective load carrying capability. How much value does this solar panel have, and how does that value change as you increase? What are the diminishing marginal returns of solar panels versus solar panels plus batteries versus wind plus batteries, wind and solar plus batteries? So these are some complicated and very intriguing and active area of research. Very interesting topic. Here's just a summary of the metrics. As I mentioned, there's now a push in the US and elsewhere to expand the criteria from just an event per year or event per 10 years to the amount of energy. The thought being, God, if we have a minor shortage, that's a lot less costly than a large shortage. Both was one event, but one had 1,000 megawatt hours of unserved energy, one had 10 megawatt hours, right? So that the event may not appropriately be capturing the event metric, loss of load probability or expectation metric, is not fully capturing the total size of the outage. And there are other metrics being considered as well. So behind this concept is now, so this is where I do want to make an important point. So a lot of times you hear the following, when I mean argument, chain of reasoning. Reliability is the most important thing, right? It's hard to, on this topic, resource adequacy, almost always the kind of the opening statement, the opening prayer is, there's nothing more important than reliability. I've heard it a million times from FERC chair commissioners, from very prominent, very well-respected people. Nothing is more important than reliability of a power system. Well, I understand the point. What they're saying is it's very important, but of course it's not the most important thing, right? There's a limit to what we do, right? We have a one time in 10 years reliability, resource adequacy. We operate the system to N-2, or N-1, number of system components, -1 number that can fail, and the system maintains reliability. We could operate to N-N. That would just be a very expensive way to operate the system. We could have a one time in in 1 day requirement, or one time in 5 years, one time in 1 year, right? The resource adequacy requirement could be much stricter than it is. So presumably behind the fact that we don't operate to n-n or one time in 1 day, reliability metric is cost is important, right? Same reason why, speed limits, we don't drive at 5 miles an hour on the highway, right? We accept a trade-off between safety and speed, between time and safety, cost and safety. Now, maybe we shouldn't, maybe the metric should be somewhere else. Maybe it should be one time in 5 years, and maybe we should operate to n-2. But regardless, once you've opened that discussion, you've recognized, and when I mean economics broadly construed, the social cost, the cost to society, health, safety, loss of industrial activity, uh, public safety, all those things combined, not just loss of industrial productivity, the fact that we had to shut down a factory, but the fact that without electricity, there's a cost to human life, for example. So the metric that people use is this value of lost load. There's different ways to interpret it, from a literal cost to just an oversimplification but useful number, to just some approximation that we use for planning purposes that we don't take literally, but at least acknowledges the fact that we're trying to do a trade-off. Okay, so here's another wrinkle. So far I built up a resource adequacy model. I pointed out some of its limitations. If you get the forecast wrong, the challenges of including battery, wind, and solar, the fact that these reliability metrics don't capture everything. They make implicit assumptions about the social costs of not having electricity. Maybe those assumptions should be explicit. Maybe different metrics or combination of metrics are used. But another dimension, and I mentioned this in the context of PJM, is that the industrial structure also matters. So as I mentioned, PJM in much of the US has a formal and organized wholesale electricity market. And with the exception of Texas, well, and they have some means of addressing when demand exceeds supply. In PJM, it's a capacity market, a capacity requirement, and that is causing its issues when there are times of shortages. In Texas and ERCOT, the way that works is they just let prices get very, very high, which would not be allowed in PJM, for example, energy prices. In different parts of the world, they do this differently, and that falls under the bucket of capacity remuneration mechanisms. How do you pay generators or utilities to have excess capacity to meet the one time in 10 years, that capacity margin that the engineers calculate? There's volume-based, quantity-based, if you're an economist, or price-based. So PJM is under voluntary base, volume-based, quantity. Texas is basically a price base. Then PJM is market through capacity markets, but then there's other ways to do it as well. So my point is not to go through each one of these or the merits or demerits, but just to kind of provide the horizons of options, policy options, to address this very real problem when there's more demand than supply, and how those options change, or the universe of options, depending if you're in a market base versus a more traditional integrated, completely regulated utility that may be owned by the government or large and private owners, publicly traded, but it's building its own and operating its own system to these reliability standards. The rest of the presentation is kind of my view, and I won't go into it, of how we should change resource adequacy models and improve them to better inform policymakers. So I'm definitely happy to talk about those issues now or offline. But I think now's a good time to turn it over to a Q&A, I guess first with your cohort of students, and then to the broader audience. But again, thank you to Rudy and Susan and the team at Lehigh University, and of course, all the students as well.
Thanks a lot, Frank. And so, very interesting presentation. Um, So as I said before, I want to open the floor to students in the seminar. Students, please unmute yourself, introduce yourself, and please ask your question. So,
I have a question also. So
I want to. Hi, I'm Selena. I have a question about the way of measuring the how much resource there should be. What do you think is the most important categories to consider for the resource adequacy?
Okay, so I mean, my view is the resource adequacy criteria or criterion should account for, although it's difficult to do, the underlying social costs associated with a blackout. Now, that's not just my view. If you open up any basic engineering textbook where they're talking about power system reliability or reliability of producing widgets, or there's a trade-off between the cost of redundancy, resource adequacy, and the cost of not having enough electricity. Those are both real costs, and they should be traded off. Now, how to do that is a challenge. It's not an easy problem, otherwise it would have been solved. I think, to me, the more pressing problem that I didn't get into in terms of these resource adequacy, although it's revealed or highlighted by wind and solar variability. So if the wind dies down, many wind farms in a region, the wind affects a large geographical space. So there could be 5 or 10 wind farms who are affected, maybe not exactly the same way as the wind slows down or increases. Same thing, maybe to a lesser extent, cloud cover. That's an example, and the industry is now called a correlated issue, that the correlation of wind farm production is positive, right? So where one wind farm is producing, it's probably likely that nearby wind farms are producing, and vice versa. They're positively correlated. There are many other types of these correlations, or maybe a better term or a broader term is common cause failures, that affect generation. Another good example is cold weather. Power plants are mechanical. When they get cold, they fail, right? We all know that. We've known this since the dawn of time. And therefore, if you assume, which many of these models have, particularly up until maybe recently, that the failure rates of an individual power plant is independent. Think from probability, from your probability class. I roll a die that's independent of what the die I rolled 10 minutes ago, right? The outcome. They're not independent, they're dependent. Cold weather, regulatory policy, could be union issues. The British in the 1950s had strikes in power plants. There's a whole range of things. And if you have a high reliable system that depends on thousands of components, generation units, if there's a failure mode that takes out 50 to 100 at a time or more, that substantially reduces the reliability and therefore the resource adequacy. That means you need a lot more spare capacity. So I think those are the two issues I would highlight: the explicit incorporation of social costs and the more explicit and uh, incorporation of potential dependent failures or common cause failures.
Thank you.
questions from students in the audience?
I have a question. My name's Adam, by the way. So my question is going back to the load growth uh, forecasts for the next decade, and it also relates back to resource adequacy modeling. So with regard to data centers, are these models considering limits to both the design and supply of computer chips, specifically in the US?
So no, that's a good question. So there's several ways. I, so one is, does the forecast of load growth for data centers, does that forecast that are exogenous to the model, right? So the modeler gets that, PJM gets that from however they get it, from a vendor, from talking to people, input from their utilities in their region who are getting these requests. Does that forecast consider other supply chain limitations? So the fact that, the data center won't be built if there are not enough chips. So best practices would be presumably yes. Presumably those forecasts are, depending on the time period, consider supply chain issues such as computer chip availability. There's another part to the question. At first, I thought you were getting at, maybe you are. Does it consider the efficiency of the chip? So,
Right. Yeah.
and so again, I think implicitly it does. I mean, the assumption is if I develop a data center, I show up at my local distribution company, I say I want a 1,000 megawatt data center, presumably that request is based on the types of chips and my business model that I'll be running. And therefore, my 1,000 megawatts assumes a certain number of chips. Now, the question is if in 2 years the chips get more efficient, do I still run 1,000 megawatts but a lot more computer chips, or do I only run at 800 megawatts? So that gets into the variability of the load forecast. And those issues, well, have been widely discussed. The question is, okay, how do you do that, right? How do you really consider that in the load forecasting? Yeah. There's Jevons paradox, a widespread paradox. You lower the price of electricity. So things get more efficient, and you would think, well, what does electricity demand increase when things get more efficient? Well, you have more money to spend, right? So in the 1960s, a family would have one TV. Now they have 20, 15 to 20, screens in their household of various sizes. In part, we're just more efficient producing electricity and the computational behind it. So even if the data centers get more efficient, one argument is, well, we use up even more electricity, right? Because we can do more.
Thank you.
Okay.
I have a question.
Yes, go ahead, please.
Let's say we allow data centers to bring their own generation, one that impacts the demand response, because from my understanding, they can be used for load shedding as well. But what happens if there's no load to shed? If they're not there on the grid?
Yeah, and
Or are we trying to say that if we remove data centers, then the grid is very stable?
I'm not sure it's so black and white. I think so. One open question is how flexible are data centers?
Okay.
That depends on a variety of things. Different owners and developers of data centers have different business models, and therefore they have different views how they would operate their data centers. So it depends in part on the business model and even on the owner. So Google has a very different view, I believe, than Microsoft on this issue. Another issue is how the data center is designed and built. Does it just have backup generators, or does it have, its own standalone power plant nearby, or, at the same location, co-located beyond just, 100 diesel generators? And its policy and willingness to transfer, to use that co-located or backup generator. Another depends on how the owner operates a fleet of data centers, so that when they get a request to process something, a map, request, or a business, request, the airline reservation, how they dispatch that request to the 20 or 30 or 40 data centers they own throughout the US or the world. The question PJM is facing is, if we interconnect all these proposed data centers, and if that large amount, that 30 gigawatts or something like that, is interconnected, in the short run, we may have to do involuntary load shedding, where PJM tells its utilities in its footprint, PPL, you have to disconnect, 500 megawatts of load for 2 hours. And peeping out just goes off and opens up a breaker, so to speak, and disconnects 500 megawatts of load. That in order to bring supply and demand back into equilibrium to avoid a cascading outage, a blackout. So then the question is, who's first on that list? So do you do data centers first? Do you create this new category of service where the large load doesn't purchase the additional capacity, but as a benefit of saving that money, it's at the top of the list? Or do not interconnect data centers and just say, you got to wait 2 more years. I know you want to interconnect in 2026 or 2027, but we won't have enough supply to 2030. You just need to wait till 2030 where we have sufficient generation plus capacity margin. So I think those are the options people are trying to think through. Does that help?
Okay, it does. I have a follow-up question. Would it be a terrible business model to just have data centers completely off the grid and have them fully dependent on their own energy?
They could do that. They would have to build a lot more. Their capacity margin for a island data center, standalone island data center of 1,000 megawatts would have to be, maybe 40% capacity margin. So they would have to have 1,400 megawatts of excess of total capacity to meet the same one time in 10 years as PJM with 15%. So one reason we interconnect is the law of large numbers, we're leveraging that. So, PJM is about, 200 gigawatts or so roughly of installed generation. I could be wrong, but of something like that, and a peak load of whatever, we saw the numbers, 180 or whatever the number is. The fact that a large generator is only 1,000 megawatts, you spread that risk over a large system, 150 gigawatts of load, for example, you need much less reserve margin or capacity margin than for a 1,000 megawatt island. So this is a well-known, it just comes out straight out of calculating simple probability combinations. So the reason data centers want to connect to the grid is it's cheaper if they can get reliable power, because then they only have to buy 15% reserve as opposed to 40%.
Okay, thank you.
Questions from Abigail. You had your hand up. Go ahead with your
Yeah,
question.
I do have a question. So my dad used to work at a data center, and they were an essential service during COVID lockdown thing, so they got to keep working because they served hospitals. So my question is, if data centers were first on the list of people who had to be disconnected when there's too much demand, would there be like a separate category for data centers that serve hospitals, or like
Yeah.
I'm not sure how that would be.
Right. So then, yeah, no, I think everyone recognizes critical facilities and their support. So you can't run a modern hospital without data center, right? They can't check in because, if you've been to hospital recently, hopefully not, but, you're given a barcode and off they go, and everything they do, right, is the nurses, the doctors, so forth, the admin people requires computation, right? Pull up your billing, your records, the chest x-rays are now electronic and so forth. So presumably those data centers or parts of data centers would be identified as you did the example you gave.
Okay, so I didn't realize you could do parts of data center, because I was
well,
also wondering, like, if that was the case, then
I
like
mean,
would all data centers just have this token tiny bit?
right. Um, Yeah, no, but, I mean, I don't know if they do, if someone recognizes and how that's done. Presumably the states have and utilities identify critical facilities, they establish communication channels, they identify like a hospital's load, not all of its load is critical. So a hospital may be running a 10 megawatt hospital, decent sized hospital, but only 5 megawatts is considered critical now. And so when they do the the planning and the operationalized load shedding, they would only serve, maybe part of a hospital. So presumably, I don't know if they do for a fact. I would suspect they do, but I don't know. They would do the same with a data center or a pharmacy or a police station or emergency center.
Okay, awesome. Thank you so much.
Okay. Questions from students?
I have a question. Is there a role for FERC or NERC to kind of coordinate or track what data centers are kind of being planned where? Because you mentioned this earlier, how a data center can be planned, can look into different areas. And if there isn't necessarily communication between utility A and utility B, or ISO A and ISO B, it might seem like there's two data centers being built, where in reality there's only going to be one.
So I believe there's recent legislation, maybe it passed in Texas, to do this. The ISOs and RTOs are now being put into this role, because what they do is they develop a forecast for the region with input from their utilities, electric distribution companies within their footprint, and roll up interconnection requests of data centers and everything else, and retirements of an auto factory, whatever, into the load forecast. The challenge is that when it goes across state lines, right? If Pennsylvania made a requirement, does Illinois or Ohio have the same requirement data? You have to do it 18 months ahead or 12 months, or this definition of what capacity is, or so forth. Or so that's a concern. The other is just the strategic nature. I'm not trying to be it's just any business, I'm not assigning this to large loads or data centers. It's strategic about where its operations are, right? For competitive advantage. And they also may still be planning, right? We're going to develop 10 data centers. They get new information. We're going to develop 8. New information. We're going to develop 11. We re-rank the order, right? I mean, they're learning more information about their supply chain, utility information about the time and cost to interconnect. So they're updating their portfolio of data center investments, so to speak, or developments, just for practical business reasons. So that's a challenge. And, they want to be able to do that. And if there are requirements that are confidential, to respect that. The other piece, so one way is people then just derate a forecast. They just say, okay, if there's 1,000 megawatts of data center requests to be interconnected in 2030, PJM applies 50%. We only assume 50% will be developed because some will go fall off the development path for whatever reason. They're duplicates, they're not economic, supply chain issues, whatever. We don't know why, we don't care. We just pick a number and we update that number over time. Another is to require data centers to have, quote, money in the game, skin in the game. So maybe the electric distribution company would report the data centers that are requested interconnections that have made deposits on the interconnection equipment, which is no small amount of money to interconnect, right? That presumes some level of seriousness, or they have the right environmental permits, or they control the land, right? They're not just, so there are other ways to check skin in the game, and there are many different ways to kind of weed out those that are more speculative for whatever reason versus those are more likely. But there's a lot of work on how to do this to be done. The state level, should FERC do this, or EIA, the Energy Information Agency, PJM, the RTOs? Yeah, it's a great question.
Thank you so much.
Yep.
Okay, I'll open the questions to the general audience. Please unmute yourself, introduce yourself, and ask the question, please.
Hi, Frank.
Go ahead, Alberto.
Hey, Frank, thank you so much for the presentation. That was very interesting. I had a question in terms of the mechanisms that are going to enter into all of this resource adequacy. So you were talking about the traditional way in which we think about these resources, right? So which And you mentioned the complications of having, for example, a storage or having solar or things like that. We're moving towards having more distributed resources, right? So just like to put it into big buckets, right? Like, like I think that a lot of the resource adequacy exercise has been very supply driven, right? Like you have all of these kind of generators, like could they be renewable or they could be conventional? But we might be, and this is where enters the stories that you were mentioning, we could be like entering into a stage in where we're going to be having more aggregators that maybe are going to be exercising some scheduling of the demand side and maybe extracting more flexibility from the demand side. In your conversations with people, like how does this inclusion of the demand side resources or of new participants enters typically in the resource adequacy exercise?
Yeah, no, that's a really good question. And I think in a good place to look at is ESE, just in general, but they've done a lot on resource adequacy and kind of the evolving models. I guess, Electric Supply Integration Group, and much of their stuff is available for free, their reports and all of their videos. So they may have a report on the demand side. First of all, people recognize if you can get demand response, but people have known this since the start of Edison. I mean, so the notion that if you have demand response for any capital intensive system, that's really helpful, right? If not everyone has to go to the airport the day after Thanksgiving, that's really helpful. You don't have to build as many highways, right? Or, that's why we have matinees at movies and senior citizen discounts at restaurants to get, spread the load. So that's a well-known, although somehow we seem to want to relearn this and be pleasantly surprised that we've learned something that, I think a French engineer figured out right after World War II, if not sooner. So the question is, how to model it. So then that gets into issues. What are the real business model of these different data centers? What are the different data center business models? How firm is their load? How dispatchable is their load? What is it meant by their capacity? Are they running at 100% nameplate? What their own generation, whether it can do as part of it. If it's behind the meter, there's less visibility. That adds, if you're PJM trying to figure this out, now you have less visibility. Um, uh, so basically, I would say the demand curve for reducing demand under different conditions, such as right now, you have to reduce it versus you have an hour's notice versus you have a day's notice versus you have a day's notice, but we're not going to do it more than 3 times a year. So those are different, in my mind, kind of demand curves or valuations one would place. And what those are, so there's kind of, there's been a lot of optimism in my view. Hopefully it's correct that there's a lot more flexibility in this. We'll see. We'll see when push comes to shove, does someone build, the 1,000 megawatt data center, but only ask for 500 megawatts of interconnection. Because they can really maneuver, however they do it, the 500 through distributed generation storage, being really smart, or whatever. Now, of course, they keep that quiet, and people who have ideas on how to do this, tell you part of the story, understandably, maybe not the whole piece. So that is really tough. And then the other piece is designing. PJM and other MISO have had very prominent cases of just entities abusing demand response programs, just gaming them, large industrial customers gaming them, pretending to do something when they're not. So the whole question is, how do you design a demand response? You depend just on prices, right? I mean, if you have a market, well, if data centers want to run and pay $20,000 a megawatt hour, why not? Now you're back to, well, what about, residential customers and, the whole, so it's an open question. And I think the whole demand, the behind the meter distributed generation makes it much harder. There's more of it, you go from 1,000 generators in PJM to 10,000, 100,000 potentially, right? Just two orders of magnitude. And yeah, it's a great question.
Thank you so much. I think that's a bit related to the question that Kevin was raising. That is, well, FERC, they have like Order 2222. That is, you should be taking into account more of these distributed resources. But at the end, it's up to the whatever is the market designer, the system operator, like like whoever is dealing there. Like, what is going to be the real mechanism that they use?
Yeah, I mean, in some sense, the good news, these data centers are so large. They really look more as much as a load as a generator. I mean, particularly they could have behind the meter or co-located, the equivalent amount of generation. And their behavior looks a lot more like a generator. They ramp up and down very quickly. They could be disconnected due to a fault, as I mentioned. They're large, you know. Um, so why are large loads different? They're large. They're not me at my house. I'm not going to bring down PJM. So,
Thank you so much, Frank.
yeah.
There's a question in the chat box from Alexander Vincent. Does this load forecast reinvigorate the role of demand response programs and potentially PJM's role in these programs? Or is this really going to be state by state response?
I think it will be both. In the comments that PJM received on its proposal that I mentioned is non-capacity backload, and it had other elements, not just that. There was a lot of comments on demand response, all the issues and many more good ideas that people are bringing up. So demand response, both the RTOs have done this, and historically, a FERC chair maybe 10 years ago really pushed this. This has some legal implications because where's the retail? Because demand response is an end use customer, right? It's someone not using electricity, a final use customer. That's under, in the US, jurisdiction of the states, it's a retail customer. But obviously it affects the wholesale market. So there's a whole set of legal issues around that. But I think and then states too can design, the local distribution company or the Public Utility Commission or whatever can provide incentives or rebates or whatever, tariff design issues, real-time pricing or time of use pricing. That's in a sense a demand response program. So I think you'll see a lot more activities on both, because in the near term, although it takes time to get those programs up and running, there's some real issues, can be some issues with them. They're relatively shorter development time than building a new nuclear power plant as a more extreme example, or generation or transmission line.
There's another interesting question in the chat box from DC. DC is a person. What is the expected amount of variability in the amount of load that a data center is expected to exhibit? And i.e., how much is PJM expecting a load from a 1 gigawatt data center, for example? What kind of flexibility are they expecting?
I don't know what PJM's expecting. That's the open question. And I think the first response is these data centers are not all the same. So they have different business models. They are doing different, they may be training AI, large scale AI models that may have a different impact on flexibility. They may be a data center that has 20 different tenants that are each doing different things. The data center may be processing a reservation system, like an airline reservation system or an Amazon, ordering system, or your local, whatever, grocery store ordering system. So the activities that fall under a data center or AI center or these large computational loads vary. Moreover, the owners may have different strategies. If they have a fleet of data centers, they may be able to coordinate the use of the data centers and dispatch the data center, so to speak. So instead of dispatching generation, you're dispatching load, but across several data centers. So it really varies, and people are trying to get better numbers and understanding into this.
Okay, good. Quick question here on the demand forecast side. Have the huge needs formerly projected for crypto mining dried up?
Okay. Yeah, so crypto mining is very price sensitive. And dried up, I mean, I'm sure in some areas, maybe in PJM compared to Texas. So it's very price sensitive, is my understanding. So there's at a point, just the arbitrage they're doing, or creating crypto, what little I know, it's just not worth the cost of electricity. So there's kind of a hard threshold at some cost per megawatt hour they're not willing to spend because they won't make up their losses in volume, so to speak. So yeah, and we'll see the next interesting question, which of these different data center activities, sub-activities I've been alluding to, how price sensitive are they?
Good. Well, Frank, this is a terrific presentation. I think you're going to be kept busy for many more weeks and months and years with all the issues that are still to be discovered. So next week, sorry, 2 weeks from now, we'll have the next seminar.
Oh, sorry to interrupt, Dr. Shankar. We have 2 questions.
Oh, there was a question?
In the class.
Okay, go ahead, please. Sorry.
Okay, I'm sorry. We often discuss data centers and electrification as separate challenges, but from a resource adequacy point of view, they put pressure on the same system. So from your professional perspective, how can we move ahead, electrification versus data centers? Should we be doing resource planning, maybe moderate electrification and moderate data centers, or should we pick one over the other?
Yeah, no, I mean, it's not for me to say. You're right about electrification, and depending on different types of electrification, they have different implications for resource adequacy. They all, as you say, would stress the same system, but take electric vehicle charging. If you can do it during off-peak periods or periods where there's plenty of resources, then the resource adequacy burden is much less than, pick another industrial process, aluminum smelting or heat pumps, residential heat pumps. So all those have implications based on their demand profile for electricity that then would filter through the model. How dispatchable are? Can you dispatch heat pumps, right? I need heat in my house, but my heat pump could maybe start 15 minutes from now and not start at the same time my neighbor's does. Or same thing with electric vehicle charging. So it really depends on the type of electrification. It goes back to for the prioritization. So the push for electrification outside of data centers or additional electricity demand is greenhouse gases, electric vehicles, heat pumps. So that gets to the priority. And this goes back to kind of, what are the state's priorities? What's their trade-off, their preference between, economic development from data centers and achieving greenhouse gas reduction goals. Can they do both? What are the costs? How does it affect reliability? How quickly can they reduce emissions, and so forth?
Okay, thank you.
All right, thank you, Frank. Again, next 2 weeks from now, we'll have a presentation from EPRI, Dr. Donald Solik. It's about bats and wind turbines. You think wind turbines are having a terrible time these days. You'd be surprised to know that sometimes bats can cause curtailment. So stay tuned. Sign up for that if you're interested. It's September 22nd. And again, on behalf of Lehigh University, Frank, thank you for your presentation. And I really enjoyed it. Thank you. See you all 2 weeks.
Thank you.